Good morning. Hi, everyone. Let's get started. So yeah, today we're going to do more prefix sums. And I think homework is due Wednesday, the programming assignment. Are people able to run the code? You're able to get on the cluster? Okay, great. Thank you. Yeah, so you can post in the ed discussion if you have any issues. And the prefix sums assignment is due like next week after the exam, but I suggest that you at least look at it because there'll be some kind of question like that on the exam. So just to get familiar with the style of question. And I posted several practice exams on Canvas. So if you have questions about those, you can let me know in the discussion. Yeah. Cool. So yeah, so we're gonna do prefix sums, but I want to talk like for a minute about how you do the homework. So the only actual, maybe like the main part in the homework is, so you have to compute sum. And so you do some local computation on every processor, like n over p, you have p processors, and you have n points that you need to compute. So you do n over p computation on every processor. And that's like, that doesn't involve MPI, that's just regular C or C++. And then when you gather the result, you have to use MPI gather. And that is one of the communication collectives, which we will talk about more next time. But basically what gather is that like, if everybody has some data of size m that you need to send, this is how it works. Like this happens to be a nice power of 2. You want to collect them all onto one processor. In this example, processor 0. And so you send 4 here in parallel. So that's takes you time m, because there's m bytes that you need to send. Then you send 2m, because now these two have 2 people's data on it. So you send 2m, and then you send 4m here. And the total time for message size 1, the runtime is tau plus mu times log p, which is the height of this tree. Yes. You could also use reduce. Yeah. Yes. Sorry.
Also, like one of the questions is it asks like if MPI reduce is better, like why is MPI reduce is better than MPI gather? And like didn't really learn anything about the differences between MPI reduce and gather. So like, are we supposed to just search it online or?
Yeah. Yeah. So reduce follows a similar pattern together, I guess, except like the tree formulation is a little different. The idea of like using this log reduction is similar. So um, if you need to use reduce, that's even better because it's easier. And I guess this is the syntax for gather, but the syntax for reduce is very similar. Basically, you gather, like collect all of the data points onto one processor, but reduce is gonna add them all into one value. So yeah, you take in the source buffer, like MPI is usually like this. You take in the source buffer, take in how many as the source, you take in the receiver buffer, and you take in how many as the output. And then you have these extra things like type, root processor, and communicator. Yeah, the syntax for reduce is very similar to this. Questions? So we're going to do a lot more about communication next time, but this is like basically all you need in terms of actual MPI functionality. Yes. If you need to do local computation, like when you gather, is like you gather all of the points onto your source root processor, and then reduce is you are collecting them all into one. So it depends on the use case, like whether or not you need one result at the end, or you need actually truly like everybody's local result. Does that make sense? Cool. Yeah. Okay. And yeah, so before we move on to applications, there are some questions last time about shared memory parallel prefix. And the confusion was about the model. So to clear up the confusion, we're going to do it in binary forking, and then we're going to do a couple of examples first. So ignoring prefix sum for a second, here is an example. We have 2 for loops. Both are over n, like I goes up to n, j goes up to n, and the inner one is parallel for. And what is the work in the span in the binary forking model? The work is n squared, yes. The span is bounded below by n, right? Because the outer for loop is n. Maybe like, can I bring this up? Sorry. Okay, so one way to think about it, yeah, that's good. So the span is the longest path through your computation DAG. So like this, you have n points up to n, right? This is n. And then each one of these has a parallel 4. So like log n that you have to do before you get here. Yeah. Yeah, this would be n log n. Yes, there's a typo, but this should be n log n. You're right, because you have to do the parallel 4, and then you put, yeah, you have to go back around. So this is n log n. And then, yeah, so for this one, this has two, the work is easy. The span is, again, lower bounded by n. It'd also be n log n. Yeah, it should be n log n, actually. Yes.
Why is it n log n and not n plus n plus
Well then, so
There's a tree at the very end. The longest path is actually
Uh,
the start.
yeah, sorry. So yes, because this is actually like, so this is the first point, right? And then there's a tree of size log n, and then there's an implicit sync after the parallel 4. So you have to do this tree of log n, and then you do the next point, which is another tree of log n. Yeah. Actually, I got that confused when I was doing these, but it is actually n log n. Sorry. Yeah, so that is why the previous ones are n log n, and then so the first one is n log n because it's like this, and then the other one is also n log n because you have two inner parallel 4s, but each of those is log n, so it's just a theta constant factor alpha that. And then this one is 4, and for each one you have a parallel 4 of size log n, and then you do so each one of these loops in the parallel 4 has like a thing of size n attached to it. Yes. No, that would be n log n, I think, because sorry, let me go back. Yeah, so this one is like, it's like this again, like you have one for loop, and then each one of these iterations in the log n has another tree of log n attached, but they all happen in parallel. So like if you just had two parallel 4s, like ignoring the outer for loop for a second, if you just had parallel 4 and parallel 4, that would be span log n. Because like you would have a tree of log n like this, and then each one of these would have another tree of log n like this. But the span is the longest path through this DAG. So the longest path through this DAG is like the first tree of height log n, and then the second tree of height log n, all the way at the bottom. That would be, so yeah. So that if you just ignore the outer parallel 4, or sorry, the outer regular 4, that would be 2 log n. But because we have this outer serial 4, you have one of these after each, like at each iteration of the serial 4, and there's n of them. Make sense? Yeah. Yeah. And then this one, you have a serial 4 again. The inner one is parallel 4, and then so you have like, again, like this computation DAG of length n, and each one of these has a tree log n, and each one of the nodes in the tree has something of length n. So that is Um, it would just be no, because each of them is done in parallel. Like each of the inner for loops, each of the most inner for loops is done in
Yeah, so
parallel
it's
on this thing.
N,
Yeah,
like a span.
yeah,
They're talking about span, so that's span, right?
yeah. So it wouldn't be like
So
n,
it's N squared. Outer.
but the outer for loop is just n.
Yeah, but like it's like the same thing, like you have like N steps. And then inside and then you have to tack on like whatever is done in the inner two loops, that's span. You have to tack it onto like the outer loop.
Yes.
Like if we were to ignore the outer loop, right? What is and parallel for in the inner loop?
Yes, if you were to ignore the outer one, that would be n log n.
Yeah, then if you just add a serial loop on the outer, then it's just n. Well, I guess for x.
The inner two loops won't be n log n. It's
Yeah, it should be n.
it's n,
It
yeah.
should be n.
Because it's like a
Yeah, because it's log n plus n. Yeah. So the inner one is n. Yeah, because that's like a tree plus one thing on each, so that's log n plus n at the bottom. And then the outer one, yeah, so you have n of those, so that'd be n squared.
N times
Yeah.
log n plus n.
Yeah, yeah. Does that make sense? Yeah. Yeah. So cool. So this is n. So let's just draw the inner one first. So this is parallel 4 plus 4. So this is log n. And then each one of those has n attached to it, like that. And so the height through this thing is log n plus n at the bottom. So that's the inner two. And then you have to repeat this n times. So so this thing is theta n, because this is n plus log n. And then if you multiply this thing by n, this is theta n squared. Yeah, makes sense? Yes. Why do you need to multiply? This outermost is sequential. So if you just had the inner one, that would be n, right? Like just the inner two is n. Well, it's theta n. It's n plus log n because it's log n height through the parallel 4 and then n at the bottom. Does that make sense? And then the outer one, you have to repeat this serially n times. So that's why it's multiplied by n. So you have to take this thing, like let's say this is the longest path, like up to here. This is the end of the first time you go through the inner part. And then again, you have to attach like another log n, like this, plus n, like this. So this would be like your first iteration, and this would be like your second iteration through the outer serial 4. Does that answer your question? So you have to repeat this n times.
Oh, in the previous slides, we were assuming the future model, right?
Yeah, so I'm redoing the bounds for parallel prefix in the binary forking model. Yeah. But first, I want to do like a couple of independent examples. Yes.
We expected to know a P1 model for the exam. I'm not really sure what it is.
It's basically like binary forking minus this log factor in most cases, but in the exam, I will specify that you can use binary forking model.
So
That we should use
if
that.
it's like a P1 model, then for this unit, for example, it just won't even have a log n. That's like the same result.
So it would be at most like a log factors off. Like in PRAM, this would become 1 rather than log n. But that's the only difference. That's the main difference between the two models. But on the exam, I'll specify to use the binary forking model, which is that the main, I guess the main point of it is that the parallel fours have height log n. Okay. Cool. Yes.
This particular example, if we omit the outer for loop, we have
Uh-huh.
one parallel for and for n.
Yes.
For that, we successfully derived that like the equation would be n plus log n, the span of the n plus log n.
Mhm.
So the very first case we were seeing a similar case where there was one serial for and one parallel for. Right?
Yes, but that one, the outer one was serial and the inner one was parallel. Let me go back. Yeah, that one.
Same example, we concluded that it would be n log n.
This is n log n because the outer 4 is serial and the inner 4 is parallel. And then in the last example, when we were ignoring the most outer one, the outer one was parallel and the inner one was serial. That's the difference. Cool. So we're going to take this and we're going to do, again, the bounds for parallel prefix in shared memory. And yeah, so this is it. It's outer 4 serial up to log n, and then inner 4 parallel 4 up to n. So this is like a similar thing like this. We have the outer 4, which is n iterations, and we have one log n tree on each one. So that was log squared. Does that make sense? And I guess to clarify, in PRAM, this is log because this is just 1. But that's the only difference, like it's log factors. Yeah, and then this thing is also in this looping formulation is log squared because the outer one is up to log, and again, this one is up to n, and it follows this, like it halves each time, but still this series is log squared. Like this, it's the inner one is up to n, but the increments jump by powers of 2 every time you go around the outer one. But so you do like half the iterations of the inner one every time, but still this is log squared. And then the same for the other side, like up and down. Does that make sense? Okay, cool. So yeah, we're gonna do more applications. The first one I want to do is radix sort. So yeah, so radix sort is like this. It's time b times n, where n is the number of points you have. And basically the way it works is that you go through the bit, or bits, b is like the number of bits you have. And the way it works is that you start the bits either from left to right or right to left, depending on which way you're going. And then, so here, like you take the least significant bit and you put all the ones with 0 in the least significant bit on the left side and all the ones with 1 on the right side. And then you take the ones with the second bit, like from the right, you put all the ones with 0 on the left side and all the ones with 1 on the right side. And then you do the same for the most significant bit here. Here, I guess blue is the ones that were moving left. And yeah, you take 0 in the most significant bit, put them left of 1 in the most significant bit, and you do stable sorting on this. And at the end, your entire list is sorted. Does the serial version make sense? Like how you would do this with one thread? On one thread, you would just like, you could just check which, you would just like find all the ones that satisfy the 0th condition, and then you just shift them over. Okay, so this is how you do it in parallel. Yeah, so the hard part of about doing this in parallel is that on one thread you could just like make one pass left to right, and then you would know, you could just mark like how many with 0 in the correct place you've seen, and then move them. Like you could count which index you're going to move them to, because you know how many you've seen so far, and then you just move them after that. So you could do like 2 passes, or even 1 pass. I guess you could just do the moving directly. But that is pretty serialized because you need to know how many come before you. Yeah, so the hard part of this is knowing which positions to move it into. And to do that, we're going to use parallel prefix. Okay. So this is an example. This is the input. And this is one step of radix sort, like on one bit. So the way it's going to work is that you make this list. You want to move the even ones left and the odd ones right. And the way this works is that you set a bit vector of all the odds. So this can be done in parallel. You just examine them all in parallel. This is the complement of the ones evenly. And then you do a prefix sum left to right in parallel on the even positions. So you're trying to figure out where you want to put the even elements in the beginning. And to do that, you can do prefix sum to tell you how many have come before you on this bit vector. And then this is just how many total evens that there are, because you need that to figure out where to put the odds also. So there's two hard parts to this. One is where the even element's going to go in the beginning, and the other one is where do like the odd elements start, and also where those going to go. And we can figure this out separately with this bit vector. And once you figure out how many total evens there are, that's like the starting. After that, the odds will start, like on the right side. So then you can you broadcast the positions for the odds, which are just 4 plus the initial position. Yeah, the odd positions are, I see, the number of evens that have come before at this point. Yes, it's just the, okay, so this is the original indexes, and then the odd positions are just how many evens are there in total for you. And those are going to go to the right, and the position, yeah, and then you can do this, like the indices of the even positions are just, yeah, so these are the odd positions, like after you add the total number of evens, and then the even positions are just the initial positions that you got from the prefix sum. And then once you have the end indices, then you just assign them according to those indices. Does that make sense? Questions? Yes.
So first you do like take you get the evens, and then you do exclusive prefix sum,
Mhm.
and then you get the even positions.
Mhm.
Why like I don't really understand like the other half.
Mhm.
Yeah, I'm sort of lost.
I see. Yeah, so maybe I can say it again. So the goal is to put all the evens on the left side and all the rights, or all the odds on the right side. And you want to do it in parallel. And the hard part about it is you don't know how many, upfront, you don't know how many evens there are and odds there are. So that's one hard part. And then the second hard part is even when you're trying, even if you knew where all the evens were, you want to assign them in parallel into their correct position with no gaps. So to do that, you need to know, like for every even one, how many even ones came before you. And you can easily do that in serial because you just go left to right and then you count, like at every even number you see, how many even numbers came before you. And then that is your position in this array. And then you could make a second pass, like doing the same with the odds. And now you know, like after you've done the even pass, you know how many evens there were. So you could just make the same pass with the odds starting at where you left off. Does that make sense for serial? So so now you want to do it in parallel. And so there's two parts. One is how many even numbers are there, so you can know where to start your odd numbers. And then the other one is like the second part, which was even when you're assigning the even numbers, how many came before you for each one, because you want to do this final assignment with no gaps. This is like the filter that we did last time, basically. Like you could imagine you want to filter the evens into the beginning. That's like the first step, kind of.
So you need to do like reordering the odds, or I don't, because I don't.
No, you don't need to. You don't reorder. Like with respect to the evens or the odds, you don't reorder them with respect to each other in this step. You're just reordering like globally. You're putting all the evens in the order that they initially appeared in on the left side, and all the odds in the order that they initially appeared in on the right side. Does that make sense? Yes.
What if you have bigger problem size than the number of processes? So let's say your array is 2p. How do you do that, and how does the radix sort parallelly work?
If your array is size 2p?
Yeah, like let's say your entire problem size does not fit into. How does the sorting work? Parallel sorting work? Because it's scattering input according to position, right? And if the entire problem size is not fitting into the processes at once, then how does the scaffold work?
You would have to keep a global index across all the, like across the entire array across processors. Good question on this part.
What does the hit position be max or max?
This, I see, because you have two vectors now of like the correct positions that everybody is supposed to go in. This one is for even. You did like a prefix sum to get the correct positions for even, but not every index in this array is the correct position for everyone, because like you do prefix sum and this happens to be right for the even numbers, but the odd numbers are not going to go in the other positions. So you need to then compute a separate vector of positions for the odd numbers, which are just like their initial position. Like, so their initial position is not changing with respect to each other. So their position in the end is just going to be their initial position plus how many evens there were. Does that make sense? And so now like you have two vectors with some of the correct positions in each. And then based on whether you have odd or even, you can mask which one you show up with. Question. Yeah. And then you just keep repeating this again with the number of bits you have. Yeah. Questions? Yes. The time to find the last bit? What do you mean? What do you mean? Like, are you saying like, is the time to figure out if the bit is 1 or 0 significant? No, because you just do like bit masking. Yeah, you could just do like 1 and with the correct. You do like an and with the 1 in the correct position, and then that can tell you if it's 1 or 0. Yeah, you could also do that in parallel, like for everybody. Okay. Yeah, so this is the algorithm. We don't need to go through it in great detail because that's pretty much what I just showed in the picture. The work in the span, there's of course b times n work because you have b iterations of n times each, and then the span is b log n because you have b iterations in the outer serial loop, and then each one on the inside has span log n. Does this make sense? Yes. Yeah, b is the number of bits in each integer. Mhm. Not necessarily. Like, for example, like if you store things in 64 or 32, like 64-bit in or 32-bit in, the thing that you're storing is not necessarily like 2 to the 32 or on the order of 2 to the 32. But in the theoretical sense, yes. Good. Questions? Cool. Okay, so that is radix sort. That's how that works. And we're going to move on to adding n-bit integers. I kind of talked about this very briefly last time, but the way this works is you want to compute the sum of two n-bit integers, a and b. And yeah, so these are the bits like a n minus 1 through a0 and b n minus 1 through b0. And you want to compute a plus b, which is the sum of the bits. And you may have an extra one, like because you can get a carry. Yeah. So this is an example. This is the binary representation of these two numbers, 22 and 29. And then if you want to add them, you just like add the bits. And if you were doing this in serial, it would be easy because you need to know if the bit is going to carry over from the right. Like, you cannot just do them all directly in parallel, because if you get two ones, for example, then this might affect the next bit, like to the left. Yeah. So does the problem make sense? Like, it seems sequentialized because you need the carry bits that come in. And this is how you can get. So S. This is like some pseudocode for it. S is the sum bit, like in the actual result, and C is the carry bit. And S depends on C minus 1. And also I depends on Ci minus 1 as well, because both the sum bit and the carry bit out depend on the input. So I guess the point of parallel prefix is like if you have problems that look sequentialized, if you look at them in the right way, or if you like decompose them in the right way, they can become parallel. Yeah. So the problem or our goal is we want to compute all of these carry bits in log n span using parallel prefix. Okay. Yeah. And the way this is going to work is the carry bit is going to be decomposed into two cases. First one is generate, which is whether or not the carry in is 1, you're going to generate an output. And you can get this by just A and B. Like if both of them were 1, then you would always get something out. And the other one is propagate, which is if you get a carry in 1, then you will get out a carry in 1. Carry out 1. And then you can get that by A or B, or AI or BI. And these are the two cases that you can get a carry out bit. And if you, yeah, so we can express every carry out bit I as generate, which is always we're going to get a carry out, plus whether or not we got a carry in times P of I, which is the propagate bit. That make sense? Okay. Yeah. And so we can write this recurrence. Carry out of 0 is generate plus propagate of Ci minus 1. And Ci minus 1 we had up front. That was just like the base case. That's 0 because you're never going to get a carry in at the most base position. And then Ci, you can write it recursively as C of 0. But we have an expression for C of 0. So you plug in this expression for C of 0 up here into here. And notice that these are all things that we can compute in parallel. Like we have propagate and generate can all be, those are independent of carry in or carry out. Those are like just based on A and B. So you can compute all of these in parallel, and we have C negative 1, or C sub negative 1 already up front. That's like the base case. So you can keep doing this. You keep unrolling this recursion, because now you like C sub 2 would have an expression, would include C sub 1, but you just plug in the expression for C sub 1. And yeah, you can express this with matrix multiply, like this, kind of like we did for fib. And yeah, you have this constant, or not constant, but you have this thing that you can compute all the P and G in parallel. And then the base case is just 0, 1. And that is, yeah, that's how you do the addition based on the bits. That makes sense? And then you compute this thing with parallel prefix. Yes. We're multiplying a matrix I times. Well, it's a small matrix. The matrix is, you can do this entire thing for all I in parallel. Like for n of these matrix multiplies, you could do this in theta n work for all I up to n. So it is, I guess it is work efficient in the sense that like if you plug in any of the parallel prefix algorithms we had that are work efficient, then you could do this in theta n time. Of course, you can do this serially also in n time, like doing this matrix multiplication. But if you were to do it serially, then you might as well just do the direct bit manipulation like that we had in the previous slide. This is this formulation is just to make it easier to do it in parallel, but like you could imagine just doing you don't want to directly do all this unrolling. Like you can do all these expressions, of course, like by unrolling the recursion, but you don't want to do all of those in parallel because that's not work efficient. Like a lot of them are going to include repeated computation. So that is why you cast this as matrix multiply, because you can reuse the repeated computations. Yes.
Where is prefix sum used?
Prefix sum is used in this matrix multiply because using this, like, so just look at the case for m of 0, I guess. So if you multiply this thing by 0, 1, you get the expression for C sub 0. And so on for all of these, like, for 2 by 2 matrix multiplies. And so we are applying, for parallel prefix, the operator is matrix multiplication. Which is fine because it is binary associative. Yeah. Questions? Cool. Okay. Yeah. So this is like an old idea. It goes back to the original hardware from Babbage, and this is how you can actually. This is how you do parallel bit addition in hardware. Okay. Questions? Yeah. So another application. Maybe I should move this down actually. Okay. Yeah, so you can do parallel prefix on things that are not necessarily just numbers. Like all the previous applications, we're doing it on ints, basically. But you can also do it on strings or characters or anything, as long as your operator is associative. So this application involves strings. It involves lexical analysis, which is you have a bunch of characters, and you want to break it down into tokens, which is something that you do during compilation. Like you write your code, and then you have to break it up into like what is a variable and what are your control flow and stuff like that. And yeah, so if you have a regular language, which is something that happens in a lot of programming languages, you can represent it with a finite state automata, which is like you have characters and then you have states and then the characters move you between the states. And like the compiler needs to break this down into, the compiler basically like breaks your code down into these state transitions to move you just through the control flow. And you could do this serially, like you could just read the tokens one at a time. Another way that you can do it in parallel is you have this state transition table, which is you start in some state. Here, this is your old state, and then if you read in a character, then it tells you like which state you're going to move into. Yeah, so this is like special characters like new line and space and stuff. And ideally, you would want to do this in parallel because then you could do your compilation faster. But it looks serialized, and it seems like the state transitions depend on which state you are previously. And what we're going to do is basically the same kind of that we did in the addition. We basically like we have some expression for the current state based on the previous state, and then we're going to unroll it, like unroll the expression to the beginning where we had some initial state. Yeah. So you can replace every character, like you have a string that you're trying to break into tokens, and you replace every character in your string with the array representation of it in this table. And so, yeah, basically the way it works is that like you have your string, and you're trying to read it in some sense left to right, but you want to read that in parallel because you don't want to determine your state based on it is based on every other state that came before you, but you don't want to necessarily have to compute those all sequentially. And so um, the operator now is this array composition based on this table. Like you unroll your state transition for every string. And yeah, and then you have some initial state, and then you can just index into that. Yes. State is just like in an automata. Like you have states are like what is your I guess like what is your like what are you trying to do now, or like for example in code, like if we go back to here, like a state would be like what control flow are you in of this thing, and you would move between the control flows based on the characters that you read. Like one state could be like add or like if, like branch or something, or end, I guess, like end the program. And you move between those states in your program based on the characters that are in your program.
So like current state, for example, certain number of
Mhm. Mhm.
You have to decide like how many characters. That would be
The characters, I guess the characters are given in this table. Like you read like one character at a time. And yeah, and not all of the characters transition you to different states. Like, for example, like your variable name could be arbitrarily long, but that wouldn't, no matter how long it is, you shouldn't move to the next state. Like the space would tell you to move on. Make sense?
why does one state require all the states before it? Doesn't it only need the previous state?
It does only need the previous state, but then that previous state requires the state before that one. Yeah, and then so on to the beginning. Good. Yeah. So basically, yeah. So you just unroll the expression for every character that you currently are at to the beginning of time based on like you can like these state transitions are composable. So like if you moved from like if you have two characters, yeah, if you have two characters, like basically what you're saying, you depend on the previous previous, but you can compose that. Like you can move from previous previous onto you if you merged if you like skipped over the intermediate one by using the table to like replace that. Um, Usually they would move if you have special tokens like if then, but the actual transition table is just given in characters, and you can tell when you move this, or you can tell like when you move on to different tokens, like with special like space or bracket or like equals. Um, those are like the things that break down your like if you were to parse this into a tree. Mhm.
I was kind of wondering, why are most of the inner values just like A, S, E?
Oh, yeah.
Characters to represent actual like the alphanumerical characters, it represents a state.
Yeah, like these characters in here are not the same as the actual letters that you write in your program. These are like, well, I don't know exactly what they stand for because it's given probably in the caption of the table, but these are like the the state within your program, like if or equals or something, is not necessarily exactly the same as the characters that are given. Like, for example, just alphanumeric characters, like the variable name. Like if you name a variable, there would be a state for like variable declaration, which is independent of what you call the variable. Make sense? Okay. Yeah. So another way to use prefix sums is segmented scan, which is rather than doing a prefix sum across the entire thing, you do a prefix sum on sections, and the sections are denoted by these flags. So, like, you can think of the flags as places to restart your prefix sum. So here, like, rather than summing over the entire thing, we restart the prefix sum here because there's a flag. So you start again at 3. 3 plus 4 is 7, like this. And here, you restart at 6, and here at 8. And you would do this uh, often in sparse applications. So if this was like your values array for sparse applications, and each row has some corresponding values in it in your matrix, but the rows are variable size, you don't want to necessarily parallelize. If you don't want to necessarily parallelize over the rows for some reason, like if they're too small, then you can parallelize over the entire vector by using parallel prefix. And you would use this in sparse matrix vector, like you multiply your row with some column, and you do like a dot product basically, and you can do that using parallel prefix. Yes.
So, what is the flag? What's the role of flags here?
The role of flags here, like in the actual application where this is used, which is sparse matrices, the flags would tell you where the new rows start. Like, yeah. So this would be one row's values, this would be another row's values, and so on, based on the different colors. and you want to do dot product of each row. Like you don't want to do dot product. You can't do like dot product over an entire matrix. You need to do like row by column. But so one way you could parallelize that is you would just parallelize over the rows, and you could do all the dot products in parallel like that. Another way to do it is you cut up the actual values array more evenly, and then you could do parallel prefix over that. And that may be better because if you parallelize over the rows, some of the rows may be too small, so it may not really be worth it to do the parallelization, but here you can get more even load balancing. Yes, yeah, like you could do this on the, we'll do graph representations later, but you could say this is like the values in CSR. Good. Another way to use prefix sums is you could do it in multiple dimensions. So this is like a classic application in image processing, pretty old application, but yeah, so they want to compute the summed area table, which is you have a 2D grid of pixels for image processing, and you want to compute the sum of some subrange of your grid of pixels. And of course, you can do that like if you did it serially. Oh yeah, and you want to do it for arbitrary ranges. You want to be able to query arbitrary ranges in this thing. And of course, like if you were to query it, you could always like figure out the range and like add up the numbers. But that would not be necessarily efficient because if you did multiple queries and some of the ranges overlapped, or yeah, like if they overlap or if some of them are subsets of each other, then you don't want to repeat your computations. So the problem is that you want to compute some, you have your grid of integers and you want to compute some intermediate thing where you can query and order one time any subrange in this 2D grid, or the sum of any subrange in this 2D grid. And the way you do that is you compute prefix sums in both dimensions. First, you do it every row, like left to right, and they do it every column, top to down. And then after you do that, left to right, top to down, then every entry is like the sum starting from the upper left corner, going down to here. Like this would be this thing. And so that would be great if all of the subranges started from the upper left, because then you could query that in order one time. However, not all the subranges start from the upper left. So the way that you would query an arbitrary subrange is using subtraction. You would, so like let's say you wanted this area. You would add in this area, so you would take this entire thing. You would subtract out this left part and this upper part here. We get this range. But unfortunately, now you subtracted this part out twice, so you have to add this back in. Make sense? So that's how you do it in 2D. With you just like do 4 summations using inclusion exclusion. Questions? Yeah. This has the caveat that it requires you to do inverse. Subtraction is like, here it was just addition and subtraction, but you can do it for multiplication or something. But not all, again, not all operators have inverse, like max. Questions on that part? Another thing that people often want to do on linked lists, so this is like an application regarding not necessarily integers, but more like data representations. It's called list ranking, which is if you have a linked list, you want to determine the distance that every node is from the end of the list. This is often used in like graph algorithms. And yeah, and it can, of course, be solved in linear time, in serial, because you just traverse your list from top to bottom, and then you keep track of like how many you've seen so far, and then you could invert that to get you the rank from the end. Well, if you traversed it from the beginning, you would keep a counter of like how many you've seen so far, but then once you've seen the total number, then you could just subtract. Yeah. So does the problem make sense? Like this is your array representation of your linked list, and then 0 is the end. So like this one points to 0, so it would have rank 1 because it's 1 away from the end. And then here, this 7 points to 8, so that would be rank 2 because it's 2 away from the end. So the input is a list in this array representation specifying their order. Specifically, every entry in this linked list, array representation of a linked list, is the pointer to the next one, where 0 is the end. So like 8 goes to here, 7 points to here, and so on like that. And the beginning is 4. So this is pointing to the successor, which is 4, so it goes to here. And this is pointing to the successor, which is 2, and then that points to here. And then this is like 6, so that's over there. And you want to output a list of length n that computes the rank, which is the distance till the end. Oh, shoot, sorry. Okay. Yeah, so you can do this using parallel prefix, as you might imagine. Basically, the way it works is you kind of create sublists of exponentially increasing distance. So first, everybody is like one hop. You have your one hop neighbor. And through one round of this parallel for, you get everybody to point to their second two hop neighbor, like their successor. And then so on. Like then the next round, you get distance 4 away from each other. Because now everybody, after this round, everybody is pointing to distance 2 away from you. And then in the next one, everybody would be pointing to distance 4 away because you take your successor. And this is the pseudocode. There's an outer for loop of log n because you're going to do, these are exponentially increasing. So the longest one is going to be n, and you double them every time. And then you have inner parallel fors where you basically, L is the input, you take your successor, like L of I. The work in the span, it is, this outer for loop is log n. These inner for loops are over n, so this n log n. And the span is log squared, because this outer one is log, and then the inner ones are over n.
Do we assume that we know the length of the earlier?
Not necessarily.
Because we're using log n.
Oh, I see. Yeah, you have, I guess you have the length of the array, which is the length of your linked list. Yeah. Yes. Yes. Well, I think I wrote it, but yeah. The work is n log n because the outer for loop is over log, and the inner loops are over n. Oh, why? Because there are every iteration of the outer loop, you kind of like point, rather than pointing to your next neighbor, you point to your next neighbor's neighbor.
Okay, because in the previous.
So every time you go through this serial outer loop, you point to, for every node, you have your, for every node, you point to that node's neighbor's neighbor. So in the first iteration, you would point to, like in the beginning, everybody points to their one hop neighbor. After one round of this, everybody points to their two hop neighbor. And then again, if you go again, that would be their four hop neighbor, because everybody points to their two hop neighbor. So like, then you jump another 2, and so it's exponentially increasing like that. So that's why it's log, because the maximum length is n. Sorry, another question?
And then what are you returning from this function?
You're returning a list R where R contains the distance to the end for every node. Yes.
Yeah, and just coming back to the length thing, it's important that we know the length because that's an ON operation to find out the length of a linked list.
Yes. Yeah. But here we have the array representation of the linked list. If you just had the pointer representation, it would take ON to find the length. But here we already have the, and you need the array representation as well because you can't like arbitrarily index to the pointer representation. But here we need to arbitrarily index into the successor. Question? Yes.
Are we assuming that the last node is
Yes, the last node points to 0. Okay. and everybody else points to their next neighbor, like their next neighbor. And we're trying to output this. Yeah. So the work is n log n, because the outer for loop is over log, the inner ones are over n, and the span is log squared, because the outer one is log, and the inner one is also log. And notice that it's not work efficient, because the best serial algorithm is n. You would just traverse through the entire thing. There are work efficient versions of this. I think they're randomized, but they're harder to explain, and this one is easier to understand. Questions? Okay. Yeah. Oh, of course, no. It's just they're mostly like examples because in the exam, actually in the exam, like the problems would be easier. Like you could also see on the homework, they would be similar level. These are just to kind of understand like how these look or like different cases to use parallel prefix. Yeah. I mean, yeah, it's just like to get you to see like what they look like. But if you look on the homework, like they're not as hard. Okay. So yeah, another thing that you can do parallel prefix for is called tree accumulation. So let's say we just have an arbitrary tree like this. You have nodes, and edges here are indexed with v, and the nodes are indexed with x. So we have two problems that we want to solve on trees. One, I mean, we have many, but in this example we have two. One is called upward accumulation, which is you sum up all the numbers in the subtree rooted at that node. So for example, like upward accumulation of v sub 4 is this, like 4 plus 7 plus 8 plus 9 plus 10. Like that, this entire subtree, and you can just find it for all the nodes. And we want to compute it efficiently for all the nodes. So like this is kind of similar to summed area table, like given a vertex, we could compute the sum in the subtree, but because there's a lot of repeated work, we don't want to keep doing it. We don't want to do overlapping work. And downward accumulation is the reverse problem. So given a node, you want to sum up all the ancestors. So for 7, you would, including yourself and ancestors. So for 7, you would do 7, 4, and 1. That make sense? Yeah. And the serial computation time is theta n for both, because you could just do like tree traversal, like depth first search or something. Yeah, so we want to do this in parallel and efficiently. Yeah, and the way that we're going to do this is based on the Euler tour, which is a way that you can traverse the tree, like just kind of like depth first. You look at every edge twice, in and out. And this Euler tour is like going from the left to the right. And you can write it down, like the sequence of nodes that you visit. Yes. And then, yeah, that's just this. Yeah, it is in order because we visit V1 first, up there. So we're going to use this memoization of the Euler tour to compute the accumulations. So we're just going to repeat it up there. And first we're going to solve upward accumulation, which is, again, like you want to efficiently solve the sum in the subtree. Okay. And the way that you do this in parallel is you have the Euler tour, and x is like the value on the nodes. And you put, for the first occurrence of every vertex in your Euler tour, you put its value, and otherwise you put 0. And then you do the prefix sum on it. And then it happens that to calculate the subarray sum, or like to calculate the sum in the subtree, you can do a subtraction of 2 values in the prefix sum. Basically, you're subtracting, you find like the end of your you find like the last, yeah, you subtract out the last occurrence or the index of the last occurrence of any vertex minus the index of the first occurrence, like the index into the prefix sum. And so what this is basically you're subtracting out everything that came before your subtree in the in-order traversal, and you're not including anything that came after it in the in-order traversal because that's not in your subtree. Does it make sense? Like you can compute this easily, and these are all independent of each other, so you can make, if you have the Euler Tor, you can make this in parallel. One question is, how do you know something is the first occurrence in the Euler Tor?
You can have like a bit, like a bit vector and then just put along whatever you
I see. Like you're saying when you construct the Euler Tor?
yeah.
Yes, you could do that. I meant once you already have the Euler Tor, how can you figure out, just like based on the ordering of the vertices, how do you figure out if you were the first time that we have entered that vertex in the Tor?
But then you just do the marking while you add
While you add the
like, I mean,
vectors?
like add to like add the nodes to the vector. So it's like you already have the mask, like everything is initialized to 0,
Mhm.
and then like whenever v1 for example, you see that v1 isn't marked yet, so you insert x1 in there.
Mhm.
Because v2 you see it, so exit x2,
Mhm.
and then with the second time you go to v2, you see that it's already marked, so you just insert 0.
I see. One thing that I ignored is how do you construct the Euler Tor in parallel? And we're not going to talk about that because it is maybe outside the scope, but pretend that we had a free algorithm to compute the Euler Tor in parallel. Because like if you computed this serially, you would sequentialize the whole thing. So if you had a black box algorithm to compute this in parallel, but let's say it doesn't tell you like the first time you see something because you may not know because it's in parallel. But we can get this ordering. So I'll give you a hint, like you can just figure it out from just this ordering itself by looking at what comes around you. Does that make sense? Like you just look at what is next to you in this in order traversal. Yes.
Previous element is like left or right.
Mm-hmm. Yes, good. Exactly. So there's another way to say it is like if you're the first time that you come in, then what came to the left of you has to be your parent because you're coming in from the top. So that's another way to say like you could look to your right, and if it's a child, then yeah, and if you're the last one, then the next one would also be going out. That makes sense? So you can compute this all in parallel just by looking at one to your left. Okay, so that is upwards accumulation. And then the inverse problem, which is downward accumulation, again depends on the Euler Tor. But we construct this array of values differently. Rather than putting 0 or value, we're going to put, for the first occurrence of v sub I, we're going to put the value. In the last occurrence, we're going to put negative x sub I, which is negative of the value. And otherwise, we'll put 0. And the reasoning for doing that is because in upwards accumulation, we just want to include ourselves once. And if we didn't do this negative, then we may include ourselves multiple times. Yeah. And the downward accumulation is even easier than in the upwards case. It's like in the previous one, we had to do subtraction of two prefix sums. This one, we just directly index into the prefix sum array because that will be the sum of everything that came in that ancestor path because we put in these negative values. Yeah. And here we need to figure out which one is the last occurrence, and that's the same. That's just the inverse problem. You look at the next one to your right, and if that one is your parent, then you are the last occurrence. So one subtlety, I guess, is this is not fully correct because if you look at the leaves, so let's just look at one, like x sub 10, for example. Here. because the leaves only appear once in the Euler tour, they never get subtracted out. So it works for all the internal nodes, but not necessarily the leaves. And yeah. So we're going to fix it by putting 0 on the leaf nodes. And then changing this final expression to just add in the leaf value if you are a leaf node. Questions? And you can look at the leaf, you can tell that you are a leaf node, kind of similar, like you look at your left and your right. And if they're the same, then questions? Yes.
Well then, what is the connector support? Oh, never mind.
You get?
So I was gonna say something.
Yeah, yeah. So we keep or we change this slightly by putting 0 in the leaves, and then we modify how you do the query by adding in the leaf value. Questions? Okay. We have a little bit of time, so we can just go through this super briefly. The last one that I'm going to talk about is sequence alignment. Sequence alignment is a dynamic programming problem in computational biology. And the input is a string over a CGT, which is the base pairs in your DNA. And the goal is to find, like, given two sequences, you want to find some optimal alignment, which is how close they are from, like, kind of like from an edit distance standpoint, but edit distance, like, you just start from the first position for everyone. Like, and then you can think of edit distance as like a very special case of alignment where you just align at the very beginning. But for alignment, you can like shift them over arbitrarily. So you want to find some global maximum based on these shifts of both strings, like how they line up with each other. Yeah, so you can do, for alignment, you can do gaps, which are like you put empty spaces, which is like maybe you can start this, for example, like without loss of generality, you can start the second string later than the first string by adding some gaps, if that does give you a better score. And you want to find the optimal alignment, which is the minimum number of substitution, insertion, and deletion to turn one string into another. It's kind of like edit distance, a little bit. Yeah. So for edit distance and alignment, you want to compute like the score, which is the quality of the alignment, and matches, which are like the character lines up in both strings, are good, so they get a positive score, and the other ones have a negative score. So here, a match would be 1, which is like you see the same character in the same column. Mismatch is 0, which is you see a different character in the same column. And gap is -1, so even worse than mismatch, which is you put a gap where you have this character. And then the score is just the sum over, the total score is just the sum over these scores. And you want to maximize the score or like minimize the cost, depending on how you think about it.
What if both of them are gaps and there's not a match for a gap?
You would never put both of them as a gap, I guess. Like you would only, like a gap is something that you can introduce in your algorithm. It's not like a thing that necessarily comes in with the string. So, like from the point of view of the algorithm, you'd never put gap against gap because otherwise, why wouldn't you just align the characters? That make sense? Good question. Yeah, sorry, that was unclear. The algorithm is introducing the gaps, and then at each step of the DP, you're saying like, would it help me to put a gap here or not in the scoring function? And the reason that it may help you is like if you introduce one gap, but then the rest of it was perfectly aligned. But if you didn't introduce a gap, then they would all be like mismatches, kind of like that. Questions? Okay. So yeah, so this is the problem definition more formally. You have two sequences, A and B. They happen to be different. They can be different lengths. A is of size M, and B is of size N. And then you have some scoring function for match and mismatch, which is f of a, b. And then you have a gap score or penalty, I guess. And there's a dynamic programming solution. You make a full table, approximately n by n. And at every position, Tij is the best score between what you have currently seen so far, between the first I characters of A and the first J characters of B. And you compute the score by taking the max over the 3 possible cases. So there are 3 cases. One is match mismatch, which is you look at like the diagonal upper left in your DP table, and then whether this f of a, b tells you whether or not you match or mismatched. There's a gap penalty for b and a gap penalty for a. And basically the gap is like you can choose in your alignment to introduce a gap, and so you don't like consume another character of, in this case, b, and in this case, a. You can just like add a space. Yeah, and in sequential time, it would take you m times n to fill out the table. Yeah, this is an example. Yeah, so these are your 2 strings, here and here. And to fill out the DP table, you look at your upper, your left, and your upper left. So here, A, so the initialization is just you put negative G times however many characters you've seen along the top first column and first row, because that would just be putting gaps in all the positions. And then when you start aligning the actual characters, here the match score is 2. So A happens to line up, so you would put 2 here. And here, this is like if you put a gap. You've consumed 1 character of this string and 2 characters of this string. So that means you need to put a gap here. So that's -1 for gap score. And then mismatch is, substitution is 0. So that's like you consume 1 character from each, but they didn't align, like they weren't the same. And then the final best score is in the lower right, as is common in DP. And you can get the actual alignment by tracing back through the max scores. So you have to do some additional bookkeeping. I think I'm basically out of time, but we can finish this next time. Thanks.